All right, so before we get started, again, a quick reminder, your worksheet is due tonight. Our extra credit surveys, final evaluations, these are all due tonight. So do get those extra credits before it's too late. I will be hosting extra office hour this afternoon between 1 to 3 in my office. So feel free to stop by if you have any additional questions. And well, today is our last lecture. So the structure of today, first I'll go over all the topics we went over. It's gonna be a very quick go over without any details, but I want to demonstrate in my perspective, right? How are these topics connected to each other that we went over together this entire quarter? And then the rest of the class I will use to go over some practice problem with you. So later on I'll do a vote to see which one you like the most. So we'll dive into more details into those questions. So getting started, right? So the first thing first, what is thermodynamics? This is your introduction to thermodynamics class, right? So in this lecture, in this entire quarter, we started by talking about vocabularies of thermodynamics. So this is our chapter 1, right? So in our chapter 1, we went over definitions of lots of terms, right? What is system? What is surrounding? What does adiabatic versus non-adiabatic mean? What does intensive versus extensive property mean? What's the difference between a state function and a line integral? These are the things we went over. These are the basic vocabularies we defined and we use in the entire quarter. In chapter 1, we also went over ideal gas law, where it comes from. And then from the ideal gas law, we extended that into the more general format, which is the equation of state. Right, so for example, we can write our volumetric equation of state. We can write volume as a function of pressure and temperature. Or we can write pressure as a temperature of volume and temperature, or temperature as a function of volume and pressure. The fundamental idea here is the number of mole of species, volume, pressure, and temperature. These are the terms that's connected to each other. An equation of state is experimentally determined by measuring alpha or chi. Now, that's our first lecture, right? So from there, we then diverged a little bit to discuss two fundamental laws of thermodynamics. Now, in chapter 2, we're focusing on our first law of thermodynamics. So what is our first law of thermodynamics? It's effectively saying our internal energy is conserved for a closed system at rest, no external field. Right? So the conservation of energy, put it in the thermodynamic fashion. More specifically, we typically write my du equals to q plus w, dq plus dw, where u is our internal energy, Q is a heat transfer, W is the work that's being done, right? So several things that's to keep in mind. Internal energy is a state function, and enthalpy is also a state function that we defined to be equal to U plus PV, right? And by heat transfer and the work, these are line integrals. So using this as an example, right, I want to demonstrate what is the structure here. Whenever we encounter a new state function, we typically start by looking at the definition, where the state function comes from, how it is being defined. Internal energy comes from the first law of thermodynamics, and then how it is being defined, right? Enthalpy is defined based on internal energy and PV. So you always want to ask yourself, what's the definition? You also want to ask yourself how to calculate the change of that state function. So when I say calculate, it doesn't mean you necessarily need to get a numeric answer, but know how to calculate, say, delta U for temperature change at constant pressure, or delta U for volume change at constant temperature, etc. And thirdly, we have the physical meaning. So the physical meaning part for chapter 2 is more straightforward. It is less obvious for chapter 3. So moving on from chapter 2 to chapter 3, we have our second law of thermodynamics. And using our second law of thermodynamics, which states that we cannot convert 100% of our disordered form of energy, which is heat, to ordered form of energy, which is work, right? And in combination with a Carnot cycle, what is a Carnot cycle? A Carnot cycle is a reversible heat engine or heat pump, consists of 2 isothermal processes and 2 adiabatic processes. From the Carnot cycle, we find out there must exist a function that's dq reversible over t. The cyclic integral of that dq reversible over t always goes to 0. From there, we define our new state function, entropy, right? And later on, again, we have 3 things, right? How it is being defined, where it comes from, how to calculate delta S, right? Build the reversible pathway and use the S equals dq reversible over t to calculate the delta S of a ideal gas change of state. And then the physical meaning of entropy, like what is entropy? So in the lecture after our first midterm exam, we went over the discussion on the physical meaning of entropy. So that is some constants, logarithm of probability plus a constant, right? So that probability describes what is the probability of a thermodynamic state to be happening. Right, so taken together, these are all the topics we discussed prior to midterm 1, right? So the first part of our lecture is talking about vocabulary, like definition of terms. What are our thermodynamic state functions that we care about? Define internal energy, enthalpy, and entropy from laws of thermodynamics, right? So that's our midterm 1. Now, after midterm 1, we moved on to chapter 4, talking about thermodynamic relations. Now, that chapter is a more abstract chapter because lots of people were like, why do I care, right? So what is chapter 4? So chapter 4 is the link between our thermodynamic state functions to something that we actually care, like equilibrium or material equilibrium specifically. So in entire chapter 4, we did 2 things. We started by definition of new thermodynamic state functions that's related to material equilibrium. Like G is defined as H minus Ts, A is defined as U minus Ts. Right, and in there, remember we have the graph telling us the link of my thermodynamic state functions with the position of equilibrium. And later on, we have our thermodynamic relations, right? That's our Gibbs equation and Maxwell relations. And now we have a total of 5 thermodynamic state functions. And note that what do I expect you to know? You need to know the definition, like what are these state functions? How are they defined? Where they come from? 2, how to calculate the change of these state functions. And 3, what is the physical meaning of the state function? Now, 1 and 3 are obviously more likely to appear in like a true and false problem. The calculation of the state function is typically where people get lost because we have lots of equations and sometimes you get lost in where to begin. So let's use delta S as an example to see like what do I mean when I say calculation of the change of the state functions, right? So let's start it here. We know that entropy, we can write it as a function of temperature and pressure. It's not necessarily pressure, you can change that to temperature and volume as well, right? Because temperature, volume, and pressure are interconnected with each other. So knowing that entropy is a function of temperature and pressure, what else can we do? We can write out the differential, right? So the infinitesimal change of entropy. We can write ds as a function of T and P equals to partial differential of S over T at constant P dt plus ds over dP at constant T dP. Right, so what are we looking for? We're looking for delta S. That equals to the integral of ds. So the question effectively we're trying to answer is, can I write down an expression of this partial differential equation and this partial differential equation into something that we can measure? All right, so what are these terms? These are the terms we get from our thermodynamic relationships. Right, so this one, the first one is the temperature dependence of entropy. And what is this term? This one, if you go back, that equals to my Cp over T, where Cp is my isobaric heat capacity, something experimentally we can measure. Likewise, what is my ds over P at constant T? That's the pressure dependence of entropy at constant temperature. Right, so this one you can write it to be equal to negative dV over dt at constant P, or that's effectively negative alpha times V. Right, so using the thermodynamic relationship, you can do the same for any state function you want, whether it's internal energy as a function of volume and temperature, enthalpy as a function of temperature or pressure, or Gibbs free energy as a function of temperature and pressure, right? So you can do the same for any state function we like, right? So that's why we spend so much time talking about thermodynamic relations and how to find out what is the expression of these partial differential equations as a function of something we can measure. All right, so how to solve this problem eventually? Now we can write this one again. On the left we have ds. On the right we have Cp over T dt minus alpha V dP. All right, take the integration on both ends. And what do we have? Right, so we have Cp. This is something we can measure as a function of temperature. We can give you like that expression to be like, say, maybe A plus BT plus CT squared. Plug it in and solve that integration for T1 to T2. Right. Likewise, on the right-hand side, we're talking about from P1 to P2. So what is our alpha B? Now my alpha itself is defined as 1 over V dV over dt at constant P. Right, and that's related to our equation of state. Again, that's why we keep asking you to say like, hey, give you a different equation of state. Can you solve for alpha and chi, right? Because we need these alpha and chi, we need these expressions derived from the equation of state to solve for change of thermodynamic functions. That's something we care about. Like for example, in this case, you can imagine do that calculation for PV equals nRT, or some kind of other kind of like P, maybe V minus B equals to nRT. Right, so can you solve that integration? Right, and taking together, what do we have? We have a general expression for delta S by using our thermodynamic relations. So that's what I mean by say for every thermodynamic state functions, what do you want? You want to know the definition, you want to know how to calculate the change of the state functions and the physical meaning. All right, so in chapter 2 and 3, we have sections talking about calculation of change of state functions for ideal gas only. That's because back then when we talk about chapter 2 and 3, we can only solve it for ideal gases. But after chapter 4, we're able to solve these properties from a more general perspective, not necessarily only for ideal gases. Okay, with me so far? All right, so that's chapter 4. And then from chapter 4, we start to move on talking about chemical potentials and equilibrium. So everything till now is more like we set our ground, right? What is thermodynamics? What are state functions we care about? How to play around with these state functions? How are these state functions connected to each other? And now we're moving on from chapter 5 and 6. We're applying these things that we derived so far into solving chemistry problem, or more specifically to predict how does my reaction equilibrium shift, how does my phase equilibrium shift. So some of the foundation here is the link between my chemical potential and material equilibrium. again, it's important to know what, again, for whenever you have a state function, like chemical potential is also a state function, right? So how it is being defined. So mu I alpha, that's defined as partial differential of G in phase alpha over the Ni alpha at constant T, P, and Nj not equal to I in phase alpha, right? So what is chemical potential? We went over that discussion when we compare chemical potential like temperature, right? So the temperature differences between two objects tells you the direction of heat flow when these two objects contact to each other. The chemical potential, the difference of chemical potential tells you the direction of material flow. So it works the same way. It's an intensive property that tells you what is the direction of material flow. And later on, we also linked our equilibrium, material equilibrium with my state functions, like for my state entropy S and versus time for an isolated system, right? That always increases. And for my Gibbs free energy versus time, so that's going to decrease in a closed system, constant Tp. And for A, that's closed system, constant Tb. Right, so these parts are connected to, these parts are more relevant to our true and false problem. So I'm going to pause here and do 3 true and false problems with you, so you can see why I always draw those pictures. So here are the 3 true and false problems I highlighted for you. Okay, this one. All right, so these are all relevant to talk about how does my Gibbs free energy change with respect to time, whether or not it's at equilibrium or not. So the diagram we have here, right, so on the y-axis we have my G, on the x-axis we have my time, and it comes down. We're talking about a closed system, constant temperature and pressure. Right, so with this figure here, let's just read the problem together. First one, delta G is always 0 for a reversible process in a closed system capable of PV work only. So a few things, right? It says reversible processes. So at which position you only have reversible processes? That's at equilibrium, right? So on this diagram, where is that equilibrium position? That's here. That's only reversible processes. But if we read this question together, delta G is always 0. Well, on this diagram, yes, delta G is always 0 when we only have reversible processes at equilibrium. But in here, it did not specify my constant temperature and pressure. Right, so that's why this one is false. What about the second one? The Gibbs energy of a closed system with PV work only is always minimized at equilibrium. The same logic, right? So my G is minimized at equilibrium, yes, but the question didn't specify constant temperature and pressure. And what about this one? It says for a irreversible isothermal isobaric process in a closed system with PV work only, delta G must be negative. Now, this one stated closed system, constant Tp. It also asks for an irreversible process. So on which part of my curve we have irreversible processes? So that's anywhere like here, right? So how does my delta G change around this point? So that's my, this is time, right? On the x-axis, that's time. So that's my initial, and here is my final. So my delta G must be negative, and this statement is true, right? So you first look at whether or not the criteria are met, and then you search for that point on the figure. And with this figure, you can solve like 3 problems. at the time. All right, so that's why like getting familiar with these concepts, and don't try to like don't try to jump to the conclusion too fast. It's more like, what do I know? How does this statement compare to the statement that we discussed in class? All right, so that's this part. And then from there, we start to talk about thermodynamic tables, right? So in this one, I highlighted the top part of our standard state thermodynamic properties, which is the thermodynamic appendix table we have. Now, when looking at this table, you want to ask yourself several questions. Like, what are these terms? What does standard state mean? Right? Where does this heat of formation comes from? What does this conventional entropy comes from? What kind of approximation we're using when we discuss conventional entropy? Right? In this process, we also discussed our third law of thermodynamics, saying like when temperature approaches 0, the delta S always equal to 0. Right? So these are the things you want to make sure you know. Now, that's the first part, right? Where these terms come from. Second part, how to use the thermodynamic table to answer questions, right? How to calculate delta H of the reaction, delta G of the reaction, how to use the Hess law to get a more complicated reaction setup. And then later on, in our last chapter, we discussed the relationship of the standard thermodynamic function of reactions, like delta G of the reactions, connect that to reaction equilibrium. Now, in this part, right, we defined our equilibrium constant to be delta G naught of the reaction equals to negative RT ln Kp. My equilibrium constant is defined as the product of my partial pressure at equilibrium over P naught to the stoichiometric coefficient mu I. Also, we went over our derivation of the Van 't Hoff equation, which tells us how does my equilibrium constant change with respect to temperature. And that's my delta H naught over RT squared. Right, so for this part, these are the connections between things we calculated to experimentally measurable, like equilibrium composition. We're using thermodynamics to predict what is happening at equilibrium, right? How much reactant do I have? How much product do I have? And how do I push my reaction forward or backward to get the product you like? Remember the example we did, right? Ammonia formation from N2 and H2. What's the ratio of my starting material? What kind of things I can do to push the reaction further forward? That's very important in chemical engineering, right? So that's the quick summary into everything we discussed this quarter. So this class does feel a little bit abstract at the beginning when we're defining all the terms from the laws of thermodynamics. So the first part is very abstract. The middle part is talking about relationship of these thermodynamic state functions. And at the end, we're applying things we derived to predict equilibrium composition of the reaction. All right, so that's a quick summary into things we discussed this quarter. Do we have any questions so far? Yes.
Just one reaction equilibrium again with like the Q as opposed to the K. Just repeat that again.
Right. So for Q, when we're predicting, we're going to do a problem together, right? But when we're talking about reaction quotient, what are we talking about? Imagine we have a reaction A and B at equilibrium, right? So let me say this one is my state 1. So in my initial state 1, my Kp naught 1 will equal to my Qp 1. What is my reaction quotient? My reaction quotient is defined as the instantaneous partial pressure to the power of the stoichiometric coefficient. So that means my reaction quotient itself is talking about the current state. Like, for example, in here, let's imagine I change the reaction condition by adding A. At constant temperature. So my Kp naught is not changing. So this is my state 2. So Kp naught stays the same. And my Qp will change, whether increase or decrease. And let's go over an example question together on this one. So this is one of the example questions we have in your textbook, which basically gives you an ideal gas reaction and asks you to predict how does equilibrium shift. So I'm just going to write down what we know so far, right? So first of all, we have our definition of my Kp naught to be the product of my partial pressure at equilibrium divided by P naught to the stoichiometric coefficient. All right. What else do we know about Kp? We have our Van 't Hoff equation. So d ln Kp naught divided by dt equals to delta H naught over RT squared. Right, so that's the equilibrium constant. It's only a function of temperature. What else? We have our reaction quotient that's defined as the product of my Pi, instantaneous partial pressure, to the power of stoichiometric coefficient. So since we're talking about ideal gas mixture, there are two different ways you can solve for Pi. Right? So Pi can either be chi I times the total pressure. So this one is more applicable when your pressure is constant. It is still true when your pressure is changing, but it will be a little bit harder to follow how does that product change if both your chi I and pressure are changing. Or alternatively, we can write that as Ni RT over volume. Right, so both of them are okay. What else do we know? We also know when Q is larger than Kp naught, we're expecting a backward reaction. Or we're pushing the reaction to the left-hand side. When Q is equal to Kp naught, we're at equilibrium. And when my Q is smaller than Kp naught, we have forward reaction. And let's use these relationships together to solve the problem here. All right. Let's look at the first one. What does it mean? We have temperature is decreased at constant pressure. Or I translated that to be isobaric temperature decrease. Now you look at these two terms, right? So some of them is not changing. We have isobaric temperature decrease, so the composition is not changing. My P is not changing. So what does that mean? That tells me my partial pressure is constant. So my partial pressure is not changing at that time. Or the other way to put it is my reaction quotient is not changing. All right. But my temperature is decreasing. And I know my equilibrium constant will change with respect to temperature. Now the question comes, what is the sign of my delta H? Right, so my d ln Kp naught over dt equals to delta H naught over RT. right? So in this question, if you imagine to plot my ln Kp and delta H on the same plot, let's imagine I have delta H naught negative. That tells me my d ln Kp over dt is negative. Right, so if we're plotting ln Kp versus temperature, the slope is negative. So what does that look like? That will be a going down plot. Alternatively, if we have my delta H is positive, then my d ln Kp naught over dt will be positive, right? So we're expecting a curve to be going up. So to this specific question, how do I find out? Now we need to find out the sign of my delta H naught. So you can use our appendix data, right? So from the appendix data, we can get the standard heat of formation. That is 0 for Cl2. That is 287.0 for my reactant, 374.9 for my product. So doing that calculation, we find out our delta H is a positive number. And what does that mean? So a positive delta H tells me my ln Kp increase with my temperature increase. And it decreases with my temperature decrease, right? Smaller temperature, smaller ln Kp. Larger temperature, larger ln Kp. So that means when temperature decrease, ln Kp naught also decrease, right? So originally my Kp naught and Q is equal without changing. And after the temperature drop, my Kp naught becomes smaller. So my reaction quotient now becomes larger than the Kp naught. So we're shifting the reaction towards backwards. All right, so this is the kind of question that don't try to jump to the conclusion too fast. It's very, very easy to get it wrong. Like just write it down every step along the way. All right, what about the second one? Volume is decreased at constant temperature. So volume decreased at constant temperature. Constant temperature tells us now our equilibrium constant is not changing. Right? Equilibrium constant is only a function of temperature. So I can write my Kp not changing. What else? We have volume increase. We have volume decrease. So my partial pressure equals to Ni RT over V. So with volume going down, volume is decreasing, all my partial pressure will increase. All right. So what about my reaction quotient? My reaction quotient equals to the product of my partial pressure to the stoichiometric coefficient. Now, in this reaction, what do we have? We have, well, PCl3 on the product, Cl2 on the product. So we have pressure of PCl3 times pressure of Cl2 over pressure of PCl5. So all the partial pressure are increasing at the same dimensionality. It just depending on how many number of more of ideal gas molecules are there in my reactant and product. Right, so in here, we see that Q is increasing because all the partial pressure are increasing. Right, so my Q is larger than K, thus a backward reaction. with me so far? And then what about the third one? Now we're removing my PCl5 at constant temperature and volume. Again, constant temperature, that tells us my equilibrium constant is remaining the same. And my partial pressure equals to Ni times RT over V. Now this RT over V is a constant. Everything else remains the same, but my partial pressure of PCl5 is decreasing with the number of mole of my PCl5 decreasing. And if you write out the reaction quotient, that's the partial pressure of PCl3 times the partial pressure of Cl2 over partial pressure of PCl5, and that's gonna increase because my partial pressure of PCl5 is on the bottom. Right. Again, we're predicting a backward reaction. All right. Now, part D and E, I want to put it like side by side so we can compare it directly. In both cases, we're adding helium gas, which is an inert gas, into the reaction mixture. But in problem D, we're keeping my total temperature and volume at constant, while in problem E, we're keeping the temperature and pressure at constant. So, will that be anything different? So don't try to jump to the conclusion too fast. We'll do the derivation one by one. So in both cases, D and E, right, you want to first ask yourself, how does my Kp naught change? So my Kp naught is constant for both cases. Because we have constant temperature in both cases. And then on the left-hand side, we want to find out how does my reaction quotient change. Right, so how does my partial pressure change on the left-hand side? We have my partial pressure equals to Ni RT over V. We're not adding any reactant to the mixture, only the helium, right? So my Ni for all my reactant or product are not changing. My volume is not changing, R is not changing, temperature is not changing, so my Pi is constant. And consequently, my Q is also constant. So on the left-hand side, we'll have no shift. All right. What about the right-hand side? So on the right-hand side, what do we have? We have constant temperature and pressure, right? So my Pi equals to chi I times P. Note that this I here is my mole fraction of my reactant or product. So adding helium to my reaction mixture while keeping pressure at constant means my mole fraction of my reactant and product will all decrease. Imagine you have a chamber with like one more of your PCl5, one more of your PCl3, one more of your Cl2. Now I'm adding another more of helium, right? So the total number of mole becomes 4, right? So each the mole fraction of each of my reactant or product will naturally drop. Right? So my chi I is dropping, and all my Pi will decrease. So naturally, it then becomes the same question we're trying to answer, right? So what's the number of mole? What's the stoichiometric coefficient? So the partial pressure of PCl3 times the partial pressure of Cl2 over the partial pressure of PCl5, right? So on the top, we have 2 partial pressure decreasing. On the bottom, we only have 1 decreasing. So overall, my reaction quotient will be decreasing, so promoting the reaction forward. Right, I compare these two side by side just to refresh your memory to say like, hey, be careful when answering these questions, right? So pay attention to the actual condition that's given. This one? Okay, so this one is a very straightforward answer. So in here, what do I have? I have my Ni, right? So what is my Ni? That's my PCl3, number of mole of my Cl2, number of mole of my PCl5, number of mole of my helium. Now, my total volume is always the same. So my partial pressure is only a function of Ni times RT over V. Since my total volume is a constant, my RT over V itself becomes a constant. It's not changing. So the partial pressure of my, say, Cl2 only depends on the number of mole of my Cl2. So adding helium doesn't change the number of mole of my Cl2. No, because we're not saying my pressure. My pressure is changing on the left-hand side. My volume is kept the same. So pressure is increasing at the same time while adding the inert gas in there. So here's the key difference, right? So whether you keep the volume constant or pressure constant. So that's what I mean by why we're not using my Pi equals to chi I times P on the left-hand side, because my pressure is also changing alongside with my mole fraction. So it's not easy to use this equation here. And it's the same, right? If you start by thinking about this equation, what is my total pressure? My total pressure equals to total number times RT over V. And my chi I here is Ni over N total. And these will cancel out. So these two are the same equation. All right. Yes.
So like technically your mole fraction is still decreasing.
Yeah, but your total pressure is increasing.
Yeah.
So that cancel out. All right. So again, this is a demonstration to see like what is behind my mind when we're looking at this kind of question. Don't jump to your conclusion too fast. Try to write down like what do we know at this condition? What is changing? What is not changing? Right. So using the things we went over in class to solve the problem like step by step. And I have about 7 minutes left. Let me go over one more problem with you. So I'll skip this derivation problem. This is the one like I expect you to know. That's as complicated as the derivation question will become. It's more or less just a math problem, so try it yourself and compare it with the answer key. And also the true and false problem. Again, these are the textbook true and false problems. I also have the answer provided in the annotated notes. But I want to go over this problem with you. This one is one of our practice problems saying like for a certain ideal gas reactions. Now I'm giving you equilibrium constant at different temperature. Ask you to find out what is delta H naught and delta S naught at 298 Kelvin for this reaction. And the tricky part of this question is that it asks you to state any approximation you're making. All right, so I want to go over like what is the logic behind this question, like how to approach this question. First of all, what is the question asking about? The question is asking us to find out delta H naught 298 Kelvin and delta S naught 298 Kelvin of a reaction. Right, so that's not changing of thermodynamic state. We're talking about a reaction. And reading this entire question, we don't have anything related to how to calculate delta S of the reaction. So naturally, you want to use my delta G naught equals to delta H naught 298 Kelvin minus T delta S naught 298 Kelvin. Right, and in here, this tells us in order to calculate delta S naught at 298 Kelvin, we must have delta G naught at 298 Kelvin and delta H naught at 298 Kelvin. This is by simply looking at what the question is asking about. Next step, how to calculate delta G naught at 298 Kelvin. Well, we have our equilibrium constant. So the reaction behind it is delta G naught at 298 Kelvin must equals to negative RT ln Kp naught at 298 Kelvin. Right? And do we have enough information? Well, R is a constant, temperature is 298 Kelvin, ln Kp at 298 Kelvin is 0.84. Right, so we're happy. So that's fine. It's like, okay, I know what my delta G naught is. And then the question becomes, what is my delta H naught? That's the only thing that's missing so that we can answer the question, answer this question. Right, so that comes here. Now, what else do we know? We have our Van 't Hoff equation, right? It gives us two different equilibrium constant at two different temperature. So what is our Van 't Hoff equation? That's my D ln Kp naught over dt equals to delta H naught over RT squared. Now in here, do we have enough information to solve for it? What does it look like if we write it out as an integral? Now let's move my dt to the right-hand side. That's my D ln Kp naught equals to delta H naught over RT squared dt. I'll take the integration, and that becomes the ln from T1 to T2, T1 to T2, ln Kp naught at T2 over ln Kp naught over T1. And this is entirely inside that logarithm. On the right-hand side, we're facing a problem. We do not have an expression of delta H as a function of temperature. But the question asks us to state any approximation we're making. Right, so what is a potential approximation we can make? We can say my delta H naught of my 298 Kelvin is equal to my delta H naught at 315 Kelvin because my delta T is small. So the whole point, I'm writing it this way because I'm going backwards, right? I'm telling you like how to set up this problem. We started by looking at what do I need, and I end up at this Van 't Hoff equation. I find like if I do not know anything about delta H naught, right? Can we assume it is not changing? And it is a reasonable approximation because my delta H is relatively constant when my delta T is small. And by say small, we want to make it very clear that this one delta T is only 17 Kelvin. It's either like below 30 Kelvin or it's above like 2000 Kelvin that you know you cannot make that approximation. Okay, so let's say assume delta H naught is constant for small delta T, which in this case is only 17 Kelvin. And the right-hand side thus becomes a constant over RT squared dt, right? So we can solve that integration to be about delta H naught over R times 1 over T1 minus 1 over T2. And do we have enough information to solve this integration? Well, yes, we have the Kp naught at T2. We have the Kp naught at T1. R is a constant. We know what temperature T1 and T2 are. So we can solve for delta H. All right, and then everything just becomes plug-in numbers. Right? We know how to solve for delta H. We know how to solve for delta G. And then we know how to use that information back to solve for delta S. So that's what behind my mind when I look at this kind of question. We start from what the question is asking about and think about like what kind of equation I can use in order to answer that question. All right, I'm running out of time, but again, I have office hour later this afternoon between 1 to 3, so please stop by if you have additional questions. And other than that, well, good luck studying. You have several extra credit items that's due tonight. You also have your worksheet due tonight. And well, that's all from me. Good luck studying.